All right, let's see. Let me share my screen. Video almost. All right, greetings YouTube. So the following is going to be like it's similar to these series videos I've been doing. Like it was basically like 5 questions from calculus. Some of them like it got a little bit dicey, a little bit, but it's more just like being organized and just trying to keep track of like calculations as opposed to concepts, But anyway, so the following is just me kind of going through those 5 questions, okay? From calculus. Let's see. All right. Greetings, YouTube. Beautiful Mind here. We have this question that comes from calculus. This is question 1 of a series of five for tonight. It says, consider the following function on the given interval. We have f of t equals t minus the cube root of t on the closed interval from -1 to 6. We're asked to find the derivative of the function and then find any critical numbers. Okay. So let's start with the derivative here. Okay, I don't know why I did that. All right, so we're just going to do it term by term. Again, terms are things that we add and subtract. Factors are things that we multiply and divide, all right? So this is the first term. This is the second term, okay? So the derivative of that first term, right? The derivative of t by itself is just going to be a 1. So let me see. So then f prime, we're going to have 1 minus. Now, we got the cube root of t. Off to the side, it might be a little bit easier to rewrite it as a rational exponent. So the cube root of t is the same as t to the power of 1/3. So then when we go to take the derivative of that guy, the power rule, right? The power comes down and we subtract 1 from the power. So then that derivative is going to be what? 1/3 t to the power of -2/3. Okay. So then we're asked to find, and let's just highlight that. So that's the derivative that we got. Let me see. Okay, that looks good. And then we're asked to find the critical numbers, right? So the critical numbers are going to occur at any value of t, in this case, usually I say x, but any value of t that makes the first derivative either 0 or undefined, right? So if we set this equal to 0, okay, I'm gonna set this equal to 0 and see if we can solve for t. So we got that negative power. I'm gonna rewrite that as a fraction or a rational expression. So we're gonna have 1 minus cube root of t squared. So 1/3. On the bottom, we're going to have the cube root of t squared. Okay, that's one way you can look at it. Okay, and we want to set this equal to 0 and see can we find a t here. Okay. Well, if we got a common denominator, it would be 3 times the cube root of t squared. So this 1 we're going to rewrite as 3 cube root t squared times 3. And repeat it, because remember with fractions the goal is to have the same denominator, so we're just saying something divided by itself, so it's going to be a 1, and then that way we can just subtract the numerators. Okay, so then on top we're going to have 3 cube root of t squared minus 1 over 3 times the cube root of t squared, okay, equal to 0. So then a fraction is going to be equal to 0 when the numerator is equal to 0. So now we set the numerator equal to 0 and solve. So then we're going to have 3 times the cube root of t squared equals 1. All right, I just set the numerator equal to 0, added 1 to both sides. I'm going to go ahead and divide by 3. No. Oh no. Uh-oh. Hopefully I can fix my Apple Pen. Oh, the cap just came off. And that's a crucial piece. And I got some more. Yeah, I think it's broken. Yeah, I can see where it's broken. It's not screwed. Where would it be? I'm gonna try to finish this one. Ah, ouch. Let me see. Can I write without it? And I can't write without it. Dang. All right, I guess I might have to pause this video. Okay, I'll be back. I gotta see if I can find these caps. I haven't seen those things in so long. I'll be back. All right, so we are back. I had to Jimmy rig it, but we got it working. So, okay, where do we leave off? Let's see. Okay, so we divide both sides by 3. Let me see. So we're going to have, I'm going to put it back to the rational. T to the power of 2/3 equals 1/3. Let me see. So we can raise both sides to the power of 3/2. Right? So we can do something like this to the power of 3/2, this to the power of 3/2. Okay. And essentially, these guys are going to cancel. On the left, we'll have our t. Let me see. So 3 cubed. So another way we can look at this is essentially what? A 1/3 cubed and then the square root. Okay. So 3 times the square root of 3, like this. So then square root of 3 over 9. Rationalize, right? Okay. When we do square root, we should do plus or minus. Let me see. 1 and then 4, so that's like 1 point something. Yeah, I think we should do plus or minus here. So when we said that, when we said to the power of 3/2, because that is an even denominator, we should do like a plus or minus here, right? So these are the numbers that we want to test for our critical value. So that's our derivative, okay? So right there. We'll test that plus the square root of 3 over 9, plus or minus the square root of 3 over 9 into the first derivative. Ow! Man, what is going on? Yeesh. I don't know what that is. Anywho. All right, so let me pull up my calculator. Here. Okay. So what I'll do, I think I'm going to start with the original. Go to my y equals, and I'm going to do x minus x to the power of 1/3. Okay. Then, let me see. I want to evaluate the derivative. Okay, so I went to math and then number 8 there. We want to take the derivative of that function with regards to x. When x is, let's do this minus the square root of 3 over 9 first. Minus square root of 3 divided by 9. Okay, we should get 0. Okay, that's essentially 0. because it's that -6, so that decimal is to the left by 6 spaces, so it's really, really, really close to 0. I'm going to remove the negative, and we should get, yeah, okay. So that's essentially 0. Okay, what were the other components? All right, so we got our derivative, we got our critical numbers, absolute max and absolute min. Okay, so absolute max and min, we take those critical numbers and we compare them. Well, wait a minute. That negatives, let me check that number. That negative square root of 3 over 9, I got to make sure it's in this interval. So the negative square root of 3 divided by 9 is, okay, yes, in there. All right. It's to the right of -1, so it's in this interval. Okay. Okay, so again, the derivative that we got, just copy and paste. And it's totally, everything is acting up today. Okay. Okay. So the critical numbers that we got again were plus or minus the square root of 3 over 9. And so the critical numbers, I think we need to test another one. So this is our derivative, right? The critical numbers are going to be those numbers that make the first derivative either 0 or undefined. Let me see. This is exponential decay. So in order for this function to be undefined, we would have to have, in this instance, a 0 in the denominator, all right? So remember, and I'll do this other part in I guess I'll do burgundy here. So we had that negative exponent. So remember our f prime one minus 3 times t to the power of 2/3. That's in the denominator. So then what value of t is going to make that denominator 0? So when t is 0. So another critical number that we need to consider is when t is 0, because it creates a 0 in the denominator. Okay. So then our critical numbers, we also need to consider 0. My little Jimmy Rig pen is working. So it's like I'm working with the Apple Pencil. Oh, and this is like maybe the 2nd generation. And I dropped the pencil, so all it needs is the pen tip for it to work properly, but it kind of broke, so I just taped it so that it will stay on and it's working. So I was like, okay, that's fine. Okay, so again, the critical numbers come from the values of t in this instance that makes the first derivative either 0 or undefined. So these are those numbers that I got. So then to find the absolute max or the absolute min, we need to compare these critical numbers to the endpoints, that -1 and that 6 that we were given. Again, we need to compare these critical numbers with the endpoint. So essentially what we're going to do is make a table. All right, if that's the original there, okay. So we can say what? T versus what? F of t. And so again, for absolute max and min, you need endpoints, which is what we were given. So we were given when t is -1, we found one of them we found was what? Negative square root of 3 over 9. we found 0, we found a positive square root of 3 over 9, and then the other endpoint was what, 6? I'm just trying to think. Did I forget anything else? I think we're okay. Let's just keep going. Okay. So we need to plug these values into the original and then compare our outputs, our y values. I think we have the original in there already. Let me just check. So then I'm going to call on the function. Let me see how I did that. So we started by putting the original function in and y equals. When I found the derivative, on the left side of the calculator, you'll see second and then alpha and then math. So when I hit math and then I hit up to get to the bottom quickly, number 8 was the nth derivative. And so when I was just evaluating that derivative at a given value. Now, another thing that I could do, I can check my critical values in the derivative that we found instead of using the calculator's derivative. Let me just do that real quick. So then 1 minus 1/3. Okay, negative square root of 3 over 9. Okay, then we need to say, kind of losing track of my parentheses here a little bit, to the power of a negative 2/3. I'll put it there later. Okay. So this is when we plugged in the negative. Again, our goal, we got our 0. And then if we do the positive, we get our 0. And then if we plug in 0, it should be, yeah, it should be undefined, right? Or we should get like an error. So this guy right here. If we replace that with 0, get an error. Okay. Okay, so we confirmed those based on the derivative that we found, So then now we want to evaluate the original function with these critical values. So to call on the function on the right side of the calculator, kind of in the middle is the clear button. Left of that is a button that says VARS, which is short for variables. I'm going to go to the right to go to Y variables. And then number 1 for function, and number 1 again to call on the function that I typed in. And I'm just going to evaluate these different values. So when x is -1, we get a 0. So we're saying that the original function is 0. Okay. I'll do that in burgundy. And then when when t is a negative square root of 3 over 9. Okay. We get this, I'm just going to write this approximation. 3849. Again, that's an approximation. Okay. And then when t is 0, we get 0. Let's do the positive square root of 3 over 9. Okay, I think we get the same number but negative, so then it's going to be approximately a negative 3849. Okay. And then when t is 6, 4.1829. Okay. Let's see. Okay, so then our maximum, this is our max value. And our minimum value, let's set that negative. This is our minimum value. Okay. So then let's see. So we got that derivative. We got those critical numbers. So the absolute maximum value we get is just like 4.1829. Well, here the minimum value that we get is negative 0. And that's, again, this is an approximation, 3849 when x, or I should say at x equals, or not x but t, square root of 3/9. And then we get a maximum value, 4.1829 at t equals 6. Okay. So then let me see our x's. Okay. So if we did like a window as x goes from where negative, let's go from like -2 to 7. Let's just go from -1, since -1 to 6, since that's what was given. And we'll go in steps of 0.5. Our y values, like 5 to like -1. So -1 to 5. Let's go in steps of 0.5 as well. Okay. Let's just look at the graph. I mean, I was going to plot those points, but so square root of 3/9. I forget what that was. So let's calculate the value when x is square root of 3/9. We should get this negative point something. Go to, yeah. So you can kind of see it blipping kind of at the bottom there. So when x is that 1924, it's kind of at the bottom, the lowest point. And again, this graph goes from when x is 1 to 6. And then the max occurs when the 6, you see it over on the far right. All right, if we go to calculate the value when x is 6, it's basically the far right, because that's the highest point. So based on, let me see, yeah, cube root of t, yeah. Right, so the lowest, those are the, and you know, again, this is just a graph of the original. To kind of recap what we did, we found the first derivative, and then the critical numbers are going to be those numbers that make the first derivative either 0 or undefined. And we found 3 plus or minus, this 2 comes from the plus or minus root 3/9, and then the third is the 0. And then we made a table to compare our critical values along with the endpoints, whichever one output, and we compared this to the original, whichever had the highest number, that was our absolute absolute max. Whichever had the lowest number was our absolute minimum value. And that's as far as we were able to take it. Okay. And let's just do this real quick. Yeah, sorry, we had like a, you know, a pen. I had to jimmy rig my pen to get it to work, but we got it working. Okay. And so with that, we're gonna end the session here. Well, this is the first of a series of 5, so we'll be back in just a moment for question number 2. All right, greetings YouTube, Beautiful Mind here, and we're back for the second installment of 5 questions from calculus. Let me see, so I'll just read this one off. I know it might be a little bit hard to see. It says, state the x coordinates of the inflection points of the curve below, right? So the inflection points are going to be the points where the curve goes from concave up to concave down, or vice versa, right? So like if you think about a cup, like you're holding a cup that you're drinking from, when you're holding it regular, that we consider it to be like concave up, like as it can hold the water. And then if you were to take that cup and turn it upside down and dump all the water out, we call that concave down, right? So the curves, we either consider them concave up or concave down. And so where the curve goes from concave up to concave down or vice versa, we call that a point of inflection. So for instance, in this graph, right, if we start from the left, right, the cup is opening downward, right? So initially we're saying that it's concave down. In the middle is concave up. So the point of inflection, just eyeballing it, is about here, and then there's another one over here. So first it goes from concave down to concave up, and then it goes back to concave down. So we have 2 points of inflection. Let me see. Now we could do some, like, okay, I'm trying to think to get in it, because like eyeballing it, it's about there. If we want to be exact, like I'm not sure how in depth they want you to go, because let me see, we got our zeros, right? We got what, a power 4 function. We got 3 zeros with one with a double multiplicity. So what we can do is create a function, or try to find this function and then take the derivative twice. So points of inflection comes from the second derivative, right? So if they want an exact result, then we need to try to find this function, okay? So it looks like the zeros are now, that's 4, that's 2. It's like it's -1, 2, and 5, okay? And it should be a power 4, okay? So let's see if we can find a function. Say that our zeros are -1, 2, and 5. And the 2 has a multiplicity of 2, right? So if these are our zeros, then one potential, so when we're trying to find this function, like some f of x, there's some coefficient, we're going to put it as a for right now. If -1 is a 0, then the factor is going to take on the form of x plus 1. Right, so that when we plug in -1 is a 0. If 2 is our 0, then the factor is going to take on the form x minus 2. We're going to make that one squared because it curves. It has a multiplicity of 2. And then if 5 is a 0, we would say x minus 5. Okay. So then what we would do is also go ahead and find another point on the graph. What else? Can we find another point on the graph? I mean, yeah, we kind of need another point on the graph to solve for that a. But if we're eyeballing it, then it's gonna, it's not gonna be exact. I'm just trying to think. So if we are just eyeballing it, it looks like when x is what, 1 and 3. That's just eyeballing it. It's just because, like I don't want to guess. Like for instance, I was considering this point here, but it doesn't look like it's exact where the peak is on the x-axis. I mean the y-axis. So like I said, we would need another point, and any other point looks like I would just be guessing. I'm trying to see if I can find something. So, because if I had to guess on that additional point, then we might as well just guess on the x value here. Let me see. So state the x coordinates of the inflection point. So the x coordinates would be, looks like 1 and 3 if I'm just eyeballing it. The curve is the graph of f. What? Oh. Yeah, we only got 2 points of inflection. the curve. Wait a minute. I feel like there should be some more here. Okay, F prime. Okay. The curve is the graph of F. Any of your answers is comma. I feel like there's some more here. State the x coordinates of the inflection points of the curve below. Let me see. I can't see which question this comes from. So it looks like it. I really want to click on that I there. I think it's just A. Because the difference between these different parts, and I feel like there's some more information somewhere, maybe not shown. State the x coordinates of the inflection points of the curve below. So, like for instance, it's looking like when x is what, a 1 and 3, and that's based on the graph of f from the original, right? That's where the original function goes, basically changes its concavity. It goes from concave up to concave down. And so the first one is saying that this is the graph of f, or is it f prime, or is it f double prime? Points of inflection, we get it from f double prime, but like if we were doing algebra, if we were doing calculations, but just looking at the graph, this is the graph of the original. The curve is the graph of f prime. I feel like there's some more somewhere. I feel like something's missing. Something seems weird here, like something is off. But I went with A. Because I got this information from the original, we could use f prime and f double prime, but I got it from the original. So I'm just going to go with that. If my client shows me like some more details there, if it doesn't work, we'll come back to this one. But otherwise, we're going to go ahead and kind of let that one be. For B and C, I'm not really seeing an answer. State the x coordinates of the inflection points of the curve below. Like I need to click on that I. But yeah, I feel like A is the best. Unless there's more details there. Unless it's like a multiple choice, is it A, B, or C? That's what I'm thinking it is. And that's why I went with that. Okay, so with that, we're going to end the session here, and we'll be back in just a moment for the third installment of this series of 5. All right, greetings YouTube, Beautiful Mind here. We have question 3 from a series of 5 for calculus. I'm just going to try to read directly from the screenshot. So it says, consider the following function. If an answer does not exist, right, does not exist. We want to find the intervals of increasing, decreasing. So, I mean, you could just look at the graph. But really, okay. So that information, like for instance, increasing, decreasing, and constant comes from the first derivative, right? So we have our function. We're going to take the derivative, and then we're going to use the first derivative to find the intervals over which the function is increasing, decreasing, or constant. When we take the first derivative, we find our critical values that's those x values that makes the first derivative either 0 or undefined. Then you have to, it kind of breaks the number line up into sections, and then you have to do tests in each of those sections, back in the original, or actually back in the first derivative. If the first derivative is positive, that means the original function is increasing. If the first derivative is negative, the original function is decreasing. If the first derivative is 0, that means the original function is constant. Okay? And then so once you have your critical values, then we can find our local max and min. The difference between local max and absolute max, and the local min and absolute min, the procedure that we did before, where we found the absolute max, it's the same procedure without the endpoints. So local max, you still got to find your critical values, you test them. That's your local max and min. If you want absolute max, you have to be given a close some endpoints to test. Okay. Okay, so let's just confirm this information. So we have this g of x. So I think we got it here. Okay. So let's go ahead and find the first derivative. So then I'm going to do in descending power order. So x to the power of 4, that derivative becomes 4x cubed. And then that 8x cubed, that derivative is what, 24x squared. And then the derivative of that 210, which is a constant, is 0. So then the critical values are going to be any x that makes this either 0 or undefined. So since this equation is a polynomial, it's not going to be undefined, but we should be able to find some zeros here. So what I'm going to do is set this guy equal to 0 and solve. So it looks like we can factor out a 4x squared from both terms. We're going to be left with x plus 6 equals 0. Okay. So then from here, in this fully factored form, then we see that what, either x equals 0 or x equals negative 6. These are our critical numbers. Okay, these guys. Okay. So then determine whether the original function is increasing, decreasing, or constant. We're going to plot these on a number line. And so since we have two critical numbers or potential candidates for critical numbers, then it's going to break the number line up into 3 sections, right? So let's look at that. So say we have our number line. Here's our positive x over here. Here's our 0. And here's, let's back it up. Let's see if that's negative 6. Let's put it in order. Okay, and we want to look at these in our f prime. Okay, so now if we plug negative 6 into the f prime, that's going to give us what, 0, and this also gives us 0. So hopefully you can see it breaks the number line up into like these 3 regions here. So like this is region A, region B, and region C. Right. Region A are going to be all the numbers to the left of negative 6. So we're just going to choose one number on the left side of negative 6, plug it into the first derivative, and pretty much all the numbers left of negative 6 are going to have the same sign. For instance, let's choose when x is, I'm just going to choose negative 10 because I feel like it'll be easy. I know it's kind of a large number, but so if we plug negative 6 into the first derivative, right? Sorry, negative 10. If we plug in negative 10, this guy is going to be negative. This guy is going to be a positive. A negative times a positive is ultimately going to be negative. So what we're saying, our claim is that f prime is negative in region A. So a negative first derivative means that the original function is decreasing on the left side of negative 6. Okay, so a number to test in region B, we can do like negative 3. If we plug negative 3 into our first derivative, this is going to be positive. This is going to be positive. A positive times a positive is going to be positive. So if our first derivative is positive, that means the original function is increasing between negative 6 and 0. All right? Okay, so that means that means that this is a local min. Local minimum value is occurring here because it went from decreasing to increasing. We're going to choose a value in region C, so something like any number to the right of 0, I'll just choose 1 to plug in the first derivative. If we plug 1 into the first derivative, did I do that right? Let me see. That's negative, that's positive. Negative, let me see. Yeah, that's positive, positive. If we plug in a 1, So if we plug in 1, right, this is positive, this is positive, so then it's positive. Okay. Which could be the case. So this implies that the original function is increasing here, right? So this gives us a lot of information, right? Let me see, what were we asked to find? Find the intervals of increasing and decreasing. Okay, let's see if we can confirm. So now we got that it was increasing on the left side of -6, so negative infinity to 6. Yes, negative infinity to -6, to see it there is decreasing. We got that is increasing from as x goes from -6 to infinity. Okay, I see that, so we confirm those. So we confirmed the interval of increase and decrease. We got a local minimum value, right? Okay. So now we're saying that the local minimum occurs when x is -6. So we would have to plug that -6 back into the original, right? Come on. So if I go to my y equals, let's go 4x to the power of 3 plus 24x squared. Okay. No, that's g prime. That's not the right one. So then 210 plus 8x cubed plus x to the power of 4. We want to evaluate that when x is, I think we got -6. We should get -222. Okay. So I think we can confirm that one as well. Right, so we got a local minimum value of -222 when x was -6. The max, we got no max, right? Because the max would occur where the first derivative, where the original function goes from increasing to decreasing. We didn't have anywhere where it went from increasing to decreasing, so that's why there was no local max. Okay. Find the points of inflection. So if we want the points of inflection, we need to look at the second derivative. Okay. So let's take a copy of this first derivative and kind of go from there. Let's copy, and I'll just paste it here. Okay. So again, points of inflection, we need to look at the second derivative. So we're going to take the derivative again. So then g double prime of x. The 3 comes down, so that becomes 12x squared. My new tape is, I'm still getting used to it. 12x squared plus 48x. Okay, so that's the second derivative. And then, so just like we found the critical values from the first derivative, when we're doing concave up, concave down, and points of inflection, we need to find the critical values of the second derivative. Again, because this is a polynomial, it won't be undefined, but we need to see, can we find those values of x and make this guy 0? So we're going to set this equal to 0 and solve. We can factor out a 12x from both. We're going to be left with x plus 4 equals 0. So then our critical values, or critical numbers, look like there are x equals 0 or -4. Right. So then if we put those on the number line, or here, we got 0 and -4. Yeah, let's just keep working down here. So here's our -4, here's our 0. Now we're looking at f double prime. So in the second derivative, this guy is what? 0 and 0, okay? So then this is going to break the number line up into three regions again: region A, region B, and region C. Okay. So then number to test, to the left of -4, we can test -5 in the second derivative. If we plug -5 into the second derivative, this guy is negative, this guy is negative. All right, negative times negative, double negative is positive. All right. All right. So if f double prime is positive to the left side of -4, that means the original function is going to be concave up in region A. Okay, and then the number to test in region B would be something like, let's do -2 when x is -2. If we plug -2 into the second derivative, this is going to be positive, this is going to be a negative. Negative times positive is negative. Okay, so negative in the second derivative means the original function is concave down. Okay, and then in region C, a number to test is like 1. If we plug 1 into the second derivative, this is going to be what? Positive. This is going to be a positive. Positive times positive is positive. So that means the original function is concave up there. Okay. So we got 2 points of inflection when x is 4 and 0, -4 and 0. So let me see. Points. Points of inflection. Okay. We'll say x versus f of x. So when x is -4 and 0, so then we need to find the corresponding y. I think that is correct. Okay, I think that's the proper original. So then we want to evaluate that function when x is -4. We get a -46. And then when x is 0, we get 210. So our claim is that the points of inflection are going to be -4, -46, and 0, 210. Okay. Let me get a copy of those. Okay. And then the interval where it's concave up. So right here, concave up, we got 2, -infinity to -4, and 0 to infinity. Sorry, just being a little bit OCD. Okay. Okay, concave up, concave down, and then use the information from parts A through C to sketch the graph and check your work. Okay. So basically, we're putting all the parts together, right? So we got these intervals of increasing and decreasing, local minimum value, there's no max, points of inflection, and then intervals where it's concave up and concave down. You would just kind of put all this on a graph, on the same graph, and then just connect it up with a smooth curve. In this instance, with something like this, you can also, let me see, our x values. Okay, we can just look at it here. We just need the proper window. Let's let x go from like -7. Let's go to like 3. We can go, let's go in steps of, we'll leave it at 0.5 for now. Our y values, I see a -6, I see a 203, -46. So let's go down to like -50. Let's go up, I guess we can go 300, or let's go to 325. What's our, we can go to 300, I guess. Let's see, let's go in steps of 25 on the y-axis, okay? Power 4. Something's off. What am I missing? 8x cubed. Let me go to my y equals 210. 8x cubed plus x to the 4. Local max. Let me see. It should be going up to the right. I feel like we need to zoom out some more. What was our minimum, our local minimum? -222. That's what it is. Okay. So we need to change our window. And when did that, what x value did that minimum occur? X is -6, so y, let's change our y minimum value to like negative, I guess we can go -300. Come on. Okay, let's see if that makes a difference. Let's look at that graph. Yeah, there we go. Okay. So I was kind of pausing because, you know, we have a degree 4 polynomial, right? So then what that means is that the tail end of the graph should go in the same direction. So because we had the improper window, we couldn't see that minimum value, and it wasn't, the end wasn't behaving properly, right? So we needed to zoom out a little bit more, you know, because from college algebra, you know, because it's a degree 4 polynomial, the long term should go in the same direction. So we got a proper window, we can at least see it or get a sense of it, and so, you know, you can see it, something like that. So it's increasing as x goes from -6 to infinity, right? So you can kind of see it on the left side of the screen there. So for that -6 value on off to the right, it's always going up. It's decreasing to the left of -6. So as we trace it, starting from negative infinity up to -6, it's always going down. Local minimum value at -6. So when x was -6, the corresponding y was at -222. You can see it there. There's no local max. We almost had one, I think, when x was 0, but we didn't get the first derivative to go from increasing to decreasing. Points of inflection, where it goes from concave up to concave down, we did have 2 points of inflection. So even though it's still increasing, it goes from concave up to concave down, back to concave up. Okay. So that's why we had 2 points of inflection, what you see there. And then we got that it's concave up as x goes from negative infinity to -4. It's concave down as x goes from -4 to 0, and then it's going back concave up again from 0 to infinity. Okay. So we got the image there, and then hopefully you should be able to see that as an option, you know, in the multiple choice. But yeah, so increasing, decreasing, and constant is a discussion centered around the first derivative. You got to find those critical values from the first derivative and do the first derivative test. And then for concavity, concave up, concave down, and points of inflection, that comes from the second derivative. So you got to basically find the critical values from the second derivative and then use your second derivative test to verify those. Okay? Or use the second derivative to find your intervals of concavity. Okay, and so with that, we're going to go ahead and end the session here, and we'll be back momentarily for the fourth installment of this series of 5 questions. All right, take care. See you in just a moment. All right, greetings YouTube, Beautiful Mind here. This is question 4 of a series of 5 from calculus. Let's see, so it says, consider the following. If an answer does not exist, enter D and E does not exist. We have this f of x equals x times the square root of 15. Let me get a copy of this. Square root of 15 minus x. So we want the intervals of increasing, decreasing, or constant, local max and min, points of inflection, okay? All right, so this is our original. Let's just go ahead and find the first derivative and the second derivative. So then f prime of x, we got to use the product rule here. Okay, so the derivative of the second, so the first times the derivative of the second, so the half comes down to the power of a -1/2. Derivative of the inside looks like it's a -1, so I'm just going to say times a -1. Okay, so that's the first times the derivative of the second plus the second. I'm working down here now. It's out of space. Second times the derivative of the first, which is a 1. Okay, I guess I had enough space. So again, the first times the derivative of the second plus the second times the derivative of the first. The derivative of x is 1. So these critical values, we want to set this to 0 and solve. Okay, I'm going to rewrite this. So we have this, what, 2? Let's see, 2 times the square root of 15 minus x under -x plus 15 minus x equal to 0. Okay. I'm going to combine like terms, or let me see. Common denominator, I'm going to use my 2 root 15 minus x, like this. Okay. So let me see. Well, that root is gone. So then we have this, what, negative 2x times 15 minus x over, no, that's not right. Back up. So that's gone. Okay. So we have this negative x plus, right? 2 times 15 minus x. Okay, that looks better. Over 2 times the root of 15 minus x. Okay, equal to 0. Okay. I'm just kind of simplifying a little bit more. So negative x minus 2x is a negative 3x. So then that's like 30 minus 3x over 2 square root of 15 minus x. Okay. I'm going to just take a little bit further. 10 minus x over 15 minus x. Okay. Okay, so this is what? Our first derivative that we got after simplifying. Okay. Let me check one more time. Yep. Square root 2 times negative x on top. Okay. So then we multiply by 2 root 15. Okay. So then that's gone. 15 minus x times 2 minus x. Okay. 30 minus 2x minus x is minus 3x. 10 minus x. Okay. Okay. So a critical value is going to occur at any x that makes this guy either 0 or undefined, right? So the 0 is going to come from the numerator, right? So if we set the numerator equal to 0 and solve, we get x equals 10. So our critical number. One of them we got was x equals 10. And then, because that's going to make it 0, but then also we got to consider an x that makes this undefined. In other words, that makes a 0 in the denominator, and that's going to be what? 15. Right? Because if we plug 15 in that denominator, 15 minus 15 is 0. We can't divide by 0. Okay, so these are the numbers that we need to test. So like if this was our 10 and this was our 15, we want to look at these in f prime. These should be our 0. Nope. The 10 should be our 0, but this guy is going to be like undefined. Okay, so then this breaks the number line up into 3 regions. It just happens to be 3. A, B, and C. Okay. So then a number in region A to test in the first derivative. For instance, like if we did, you could do 0, right? I think that should be a simple result. If we plug 0 into the first derivative, this numerator is going to be positive. The denominator is also going to be a positive. So then a positive divided by a positive should be positive. So we got that the first derivative is positive here, which implies the original is increasing left of 10. So then a number between 10 and 15 to test, let's test 13 into the first derivative. If we plug 13 into the first derivative, this numerator is going to be a negative. The denominator is going to be a positive. A negative divided by a positive is negative. So we got that the first derivative is negative here. And so the original function should be decreasing in region B. In region C, a number to test is what? We can do like 20. If we plug 20 into the first derivative, this guy is negative. We can't take the square root of a negative, right? So does it end? What's happening over there to the right of 15? Is there something about the domain? Does it end? It looks like it might end. Let me see the original. Okay. Okay, yeah. So the domain, right? The original we have right there at the top. That square root 15 minus x, right? We can't take the square root of negatives. So that 15 minus x has to be greater than or equal to 0. So x has to be less than or equal to 15. So it has to be strictly less than 15, all right? So region C, we got it was completely undefined in that region. So x has to be strictly less than 15, because once you hit 15, we start either dividing by 0 or getting a negative under the radical. So it seems like the graph is going to end as we approach 15, on the left side of 15, okay? Okay, so that's from the first derivative. Sorry. So we still need to find the second derivative. That was everything. So let's. Some of these do get kind of. They be kind of extra. I mean, a lot of them are extra, but Okay, so now we need to look at the second derivative. Okay. So if that's the first derivative, so it looks like we got to use the quotient. We got a lot of things at play here. We need to do the quotient rule. So then f double prime of x, low d high minus high d low over low low. So the bottom, which is this guy, the derivative of the top is like it's just a -3. So that's the bottom times the derivative of the top minus the top. The derivative of the bottom, the 1/2 comes down, so that cancels out the 2. We still have that 15 minus x to the power of a -1/2 times the derivative of the inside, which is a -1. And then we need to do all over the bottom squared. Okay. Give me just a moment. I'm going to shrink this down. Just to get it on one line. Because I definitely need to go back and check this. Guess that's decent. It's kind of irking me. Okay. And then all right. Let me check this again. And there's more. I'll try to go back and simplify it. This one, sometimes the second derivatives can be a little bit extra. So the bottom times the derivative of the top minus the top times the derivative of the bottom. The 1/2 came down and canceled. We still got the 15 minus x at a minus 1/2 times the derivative of the inside. So that's the derivative of the bottom all over the bottom squared. Okay. Let me see. Okay, we need to try to simplify this. 10 minus x, okay. We could multiply the top and the bottom by. Okay, let me just try to capture this. I'm kind of like getting sleepy, I think. So I'm thinking about by multiplying by 1 in the form of root 15 minus x over root 15 minus x. If we do that, let me see. So like if I distribute, I'm saying the top and the bottom by the square root of 15 minus x on top and bottom, right? If we do this, we're going to have to distribute, right? It should cancel out this guy and get rid of this radical, okay? And then on bottom, I mean, it's a little bit extra. Okay, let's go with it and see what happens. Okay. So my f double prime that I'm getting right now, I got a negative 6, 15 minus x, because the radical's gone. Gotta keep track of this negative here. That's gone. Double negative is now positive. We got this, what, 30 minus 3x? Okay. I think that's a good numerator. And then on bottom, we got this, what? Oh, wait a minute. Okay. 30 minus 2x times let me back up. I forgot the square. Okay. So it's going to be 60 minus 4x times the square root of 15 minus x. Okay. So a little bit extra. We're almost there. So then f double prime, I'm just going to expand that numerator. 60 plus 30 is a negative 90. Six x 30. Oh man, I hope I didn't miss something. I'm gonna just go with it. I'm gonna leave that as 60 minus 4x times the square root 15 minus x. Okay. All right. So then I am getting 3x. What is that? A negative 60? So close. 60 minus 4x times the square root of 15 minus x. That was an adventure. Now we can factor out a 3. That would make that x minus 20. We factor out a 4. You know, I don't know. Nothing really seems like it cancels, so this should be fine for our second derivative. Okay, let's go back and try to answer the questions. And I think we got increasing and decreasing, right? We got that it was increasing as x goes from negative infinity. The far left will be negative infinity up to where 10, open parentheses. We got that it's decreasing as x goes from 10 to 15, open parentheses. And that was it there. Okay. Local minimum. We had no local minimum because, you know, we went from increasing to decreasing, so that's actually a local max. Is occurring here. So local minimum should be none, and then the local max. So that occurs when x is 10, right? So we have to plug in the 10 back into the original. Would that be well, in order for 15 to be a local minimum, the original function would have to go from decreasing to increasing, right? We don't get the increasing on the other side for that to be a minimum. So for the minimum, we got does not exist. Points of inflection, let's go ahead and use the second derivative, okay? So we need to find our critical values here. That's going to be the x's that makes this guy either 0 or undefined, okay? So from the numerator, if we set that to 0 and solve, what is that, 20? So we get x equals 20 from the numerator. From the denominator, we got to get rid of any, we have to consider any x that makes the denominator 0. So let me see, add and divide, I guess it's 20 as well, right? No. Divide 15, right? Okay, it's a couple of things that play in the denominator. When x is 15, it creates a 0. So we have to consider that in the denominator because it's going to make the original function undefined. But then we also can't take the square root of a negative number. So that has to be greater than or equal to 0. So x has to be strictly less than 15. Okay. Okay. So let me see. Points of inflection. So that 15 was almost a point of inflection, but again, because we don't have the right hand side to compare it to, we just know that that's a cutoff. Let me see. Greater than, Okay, let's see. So we got this 15 minus x has to be greater than or equal to 0. Add. And it can't be 0. Okay. So the only critical number that we're really getting is 20. Because, because we had that square root. I mean, we get an infinite amount. Whenever x is less than, or whenever x is greater than is greater than or equal to 15, then we're getting an error. All right. For instance, if x were 16, it's going to create a negative in the square root, so we can't use it. All right. So whenever x is greater than 15, greater than or equal to 15, then we have to throw those out. So in other words, x has to be strictly less than 15. So let me see. Okay. Find the intervals where the function is concave up. Okay. So we got this 20. We know something happens at 15 and 20, right? So let's look at those numbers and see. Let's just see what happens on either side. All right. Let's see what happens around those numbers. Because it is a little bit weird. Let me see. So here's our 15. Here's our 20. All right. And we want to look at the second derivative. Okay. Now, these aren't official. I'm just kind of playing around a little bit here. if I did like this, say this was my region A, this is my region B. Okay. So number left of 15 to test, again, we're saying that our domain is x is strictly less than 15. So we should get some errors in regions B and C. Maybe there aren't any points of inflection. Because we only got the one region, right? Like if we choose something like 0, right? If we plug 0 into the second derivative, the top is negative. Let's see, a positive. Looks like the bottom is positive. So the second derivative is negative in that region. Let me move this over. Which means the original function is concave down. So we might not have a point of inflection because nothing to the right of 15 should work, right? Like if we tried 17 into the second derivative, we shouldn't get a result. What is that? 30 plus 21 is 51. So this would be what, a negative here. What did we say? 17. So we got a negative there. $40 plus 28, 68. That's negative. That's imaginary. See, right here, when we go to plug in our 17, we get a negative, so it stops us. Any number to the right of 15, we won't be able to use it, right? So we did get that it was concave down on the left side of 15. We got no points of inflection. And we got that it's concave down from negative infinity up to 15. The far left is negative infinity up to 15. That was concave down. No points of inflection. I kind of want to look at this graph. Oh. Let's look at this graph and just kind of confirm some of these notions. Let me fill these different parts in. The interval, ooh, I almost dropped the pen again. Like this is why I messed up now. Find the interval in which it's increasing. So we got that it was increasing from negative infinity to negative 10. That was increasing. Sorry, to 10. Let's copy. Let me paste here. Okay. Oop. Okay. Right there. Okay. Trying to let me get rid of this. We got that it was decreasing here, so we confirm that one. Okay, we got increasing there. Okay, local min and max. All right, so from this test, we only got a local max and no local min. We got a maximum value when x is 10, so we need to plug 10 into the original. So here we got no local minimum, so here we got like does not exist. The max we said occurred when x was 10. So let's go to our y equals, and we're going to put that in. We got this x times the square root. 15 minus x. We want to evaluate this when x was 10. Okay, we got a value, let me see, 2236. When x is 10, you can say 10 times the square root of 5. Let me just check. 10 times the square root of 5. Okay. Oh, you got them backwards, I see. Point of inflection, I think we got none. I didn't get a point of inflection. Because it was the numbers that I was testing were 15 and 20, but our domain restriction, we had that it had to be strictly less than 15. Let me see if I can see something else. That's a 20. We set that to 0. 60 divided by 430 is 15. I'm not getting a critical number less than 15. Okay. Let's see. So I got none. Like I got none for that one. So we're gonna look at the image and see if we can kind of confirm this out. Find the intervals over which the function is concave up. So we got concave up. Sorry, we got concave down from negative infinity up to 15. And here for concave up, we got like none or does not exist. Okay, so let's see. We got it's increasing up to 10 and then it's decreasing. Now, let's just look at the image, right? Because of that square root, I think this was kind of like making things a little weird. We got that. Let me see our window. It looks like everything is around 10 to 15. Our y values, that was like 22. So we need to go up to like, our x's need to go up to like 20. We'll go to 25. So we'll let x go from negative 25 up to 25. You can go in steps of steps of 5. Our y values, I know we need at least like 22. Let's go 30, I guess. Let's go 30. And let's go in steps of 3. Let's see, it stops, right? So remember, we said that like once it hits 15, it stops. Now let's confirm. Intervals are increasing from negative infinity to 10, right? So it's increasing up until once we hit 10, then it goes to decreasing. We got that it's decreasing from 10 to 15, okay? We didn't get any local minimum value, but we did have a local max of 10 root 5, which is like 22 something. Concave up, we got no concave up, but we did have concave down from negative infinity to 15. And then here's the image, right? And so then if it's multiple choice, you can just use this. That's really interesting. That one made me, I was like, wait a minute. I got to like process this because there was a lot going on in that question. There definitely was a lot from, the second derivative can be a pain. You just got to take your time and just, because like like that one ended up being the quotient rule, right? Low D high minus high D low over low low. So the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom square. Plus it's like 1:15 in the morning, so that's like another thing that's, and I haven't been to sleep yet. So that's making it a little bit more challenging, so you have to forgive me, but yeah. But we have an image that confirms the data that we got, right? So that's about the best we could do. Okay. We do have one more installment, so we'll be back in just a moment for that final part. Okay. Take care. All right. So greetings, YouTube. A beautiful mind here with the fifth question from an installment of 5 for calculus. We're asked to consider this function, and there's several parts. We're asked to find the vertical asymptotes, if any, find the horizontal asymptotes, if any, the intervals of increasing or decreasing local max and min values, the interval where it's concave up and concave down at any points of inflection. Okay, so these are all questions that's pretty much centered around the first derivative and the second derivative. So let's try to go ahead and find those aspects of this equation. Let's see. So let's start off with the first derivative. E is its own derivative. But then we say times the derivative of that power. Ugh. Okay. Okay. So that's what? -2 times x to the -1. When you take the derivative, the negative comes down, so that's now a positive 2x to the -2. Okay. All right. So if that's the first derivative, let me just check one more time. I'm going to go with it for now. Do we have any of those? No. It's because it's basically -2 times x to the -1. -1 comes down, so double negative becomes positive 2x to the -2. Okay. So if that's our first derivative, let's go ahead and take a look at our second derivative, or f double prime. So basically we take the derivative of this guy. So then we have to use what? The product rule. First times the derivative of the second plus the second times the derivative of the first. So the first is this guy. The derivative of the second, -4x to the -3. So that's the first times the second plus the second, the derivative of the first. We got to repeat all of that. So it's going to be what? E to the -2 over x. 2x to the -2. Let me get all of this on one line. Okay. Okay. So we have our f prime, and f double prime. Okay. Vertical asymptotes. So the vertical asymptote. So let me kind of start here. I'm just shorthand. Okay. So if our f of x is e to the -2 over x, all right, that's the same as what? 1 over e to the 2 over x, okay? So can we find a value of x that's going to make this guy, this denominator, 0? Okay, let's just set it equal to 0 and solve. So if we say e to the power of 2 over x equal to 0, I don't think we can take the natural log of 0, right? So maybe there's no vertical asymptote, right? We would get none. Because we can't find the value of x, it's going to make that denominator 0. Because when we try to solve, we take the natural log on both sides. Natural log of 0 is undefined. So I got no. So vertical asymptotes, I got none. Okay, we're going to go with that for now. Let's see. Horizontal asymptote. So basically, as x goes off to infinity, plus infinity or minus infinity. So we got a fixed numerator. Let's use this guy on the right here. All right. So as x goes to infinity, that power gets closer and closer to 0. So we have e to the power of 0, which is a 1. So as x goes up to the far right, it looks like we're getting a 1. So I'm just going to write it kind of like this. So for the horizontal, the limit as x goes to positive infinity of this function looks like it approaches 1, right? Because that goes to 0. E to the 0 is a 1. 1 divided by 1 is 1, okay? Then let's also consider the limit as x goes to negative infinity of this function. So if x is going to negative infinity, double negative is positive. E to the 0 is also a 1 still. So as we go off to the far right or the far left, it looks like the function approaches 1. Okay. So then for the horizontal asymptote, we would say what? Y equals, or f of x equals 1. Okay. For the horizontal asymptote, or I guess y equals, because that's what they have in the text. I'm going to just put it as y. Okay. Find the intervals of increasing, decreasing. So we need the first derivative. Okay, so for increasing and decreasing, we need to find the values of x that makes the first derivative either 0 or undefined. So let me get a copy of this guy. Paste. Okay. Okay. So we got those negative powers. Sometimes I feel like it's easier to see it. Like if you're dealing with a negative power, just go ahead and put it in the denominator. I feel like it makes it a little bit easier to see. It's still a little bit, kind of like all over the place a little bit, but I feel like it's somewhat easier to see. So I'm going to move those to the denominator. We're going to have what? X squared e 2 over x under 2. Okay. So the critical numbers are going to be the values of x that makes this guy either 0 or undefined. We're not going to find the x that makes the numerator 0, right? So, but we have some x's that makes the denominator 0, right? What, when x is 0? So like it looks like we're getting one critical number is when x is 0. Okay, let's keep going. There might be a little bit more there, but for right now, I'm going to go with that. Okay. So here's my positive x. Here's my 0. We're looking at the first derivative. It's going to make the first derivative undefined. Okay, so a number left of, so it breaks the number line up into two regions, region A and region B. Left of 0, let's try like a -1. Let me see, if we plug in -1 into this first derivative, this guy here is going to be a positive. -2, this is going to be a positive. Everything is positive. So I'm getting that the first derivative is positive in region A, which implies that the original function is increasing. Okay. Let's try region B. We can try 1. If we plug 1 in, all right, into the first derivative, we get a positive result here, positive result here. Everything is positive, so I get that it's increasing there as well. It could be the case. So then we're getting that there's no point of, there's no local extrema. Let me see. So this part X is to find the intervals of increase. I'm getting that it's increasing across the entire graph. And then I get that it's decreasing nowhere. Okay. I'm getting no local max or mins because we're not getting our change there. And then for concavity, we need to look at the second derivative. Now, we probably should try to simplify the second derivative. I just got there and I just stopped. I didn't even try to simplify it. I think we can simplify it some. It's going to take some effort, but I think we can do it. Okay. So let's try to simplify this guy. Let me see. Common factors. It looks like they both have this e to the minus 2 over x. They both have it. That's kind of throwing me for a loop. We add. That's going to be a 4. We could factor out a 4. Like these two with this, we could factor out a 4. Okay. Okay. So the negatives are throwing me for a little. I need to rewrite them. But in the interim, so my claim is that we can factor out what? 4 e to the negative 2 over x from both terms, okay? So from that first one, if we factor this out, what's left? That's gone here. This is gone, that's gone. We have, what's left is this negative x to the negative 3, okay? And then from the second one, if we factor out that 4 and the e, this is gone, this is gone. We're left with an x to the minus 4, okay. Okay, Okay, I'm gonna rearrange this some just to try to make it a little bit more simple. So I'm going to rewrite this as 1 over x to the 4 minus 1 over x to the third. Okay. Now we could factor out a 1 over x to the third from both. That'll leave us with what? 1 over x minus 1? Does that help us? Maybe. Okay. I'm going to account for that just to see if it helps. 4e to the negative 2 over x. We factored out the x to the third. We're left with 1 over x minus 1. Okay. Okay. Let me see. Now I'm thinking of like, let's condense it, just to get like, let me just kind of work on it a bit. So x, okay, that's going to be a 1 minus x. So we got this 4e to the negative 2 over x, x to the 3, 1 minus x, x, okay. Would that make it worse? That might make it worse. Ugh. Okay. So I'm going to leave it here. 4e to the minus 2 over x, 1 minus x over x to the power of 4. Okay. Okay. This is about the best I can do with that, trying to simplify that down. So if we want the critical numbers from here, is any x that makes this expression either 0 or undefined, right? So the 0 is going to come from the numerator being 0. Now I think that earlier we said that this part here won't be 0. We can't find an x to make that 0. But we can find an x to make this 0, which is namely when x is 1, right? So our critical number, we got x equals 1 for one of them. And then from the denominator, when x is 0. Okay. So we need to test these in the second derivative. Okay. So here's our 0, here's our 1. We want to look at the second derivative. This is going to make it undefined. This is going to make it 0. So here's our region A, our region B, our region C. Let's see. So something like negative 1 into the second derivative, what happens? This is positive. I'll have to check that later. That's negative 1. This is what, positive? And this is positive. Okay. So it looks like the second derivative is positive in this region, which implies that the original is concave up. In region B, we could do something like a half. If we plug in a half, this is positive. This is positive. And this is positive. All right, so we're not getting a point of inflection there. And let's try region C, like when x is 2. We plug in 2. This is negative. This is positive. This is positive. So it looks like the whole thing is negative. So I'm getting concave down there. So we do have a point of inflection. Looks like we have a point of inflection when x is 1. So this identifies a point of inflection. Okay. Because the original function went from concave up to concave down. Okay. So let me see. Do we have a max or min? No. Because I only got the one critical number. I didn't have any local max or mins. But I did have a point of inflection when x was 1. We just have to find the corresponding y. We got concave up. Basically from negative infinity to 0. We got concave down from 0 to infinity. Okay. And then the point of inflection, we need to find the corresponding y. Okay, so let's look at this graph. Let's list out all the different parts that we have, okay? Let me see. So for the original function, minus, yeah, we got the minus 2 over x. Okay. So for the vertical asymptotes, let me see. I think we got none there. So there we got none. For the horizontal, y equals 1. Okay. And then for part B, increasing or decreasing, we got that it was increasing over the entire domain. Is the domain all reals? Yes. No. Okay, so we got that it's increasing everywhere except 0. Because, yeah, the domain is all reals except 0 because we can't divide by 0. Okay. So I got the original function is increasing from negative infinity up to 0, and then from 0 to infinity. It's either this one or it might accept negative infinity to infinity. Decreasing, I got none. Local max and min values. I think there was none because we didn't get any change in sign of the first derivative. Okay. So no local extrema. concave up and concave down. Is that my second derivative? Let me check this again. I feel like I made a mistake with that 1/2, right? No, that's positive. Yeah, we're good. Is there an asymptote there? We didn't get a vertical asymptote. So I got that it's concave up from negative infinity to 1. So I'm going to capture concave up like this. From negative infinity up until 1. I got that it was concave down. I think it was 1 to infinity. And then the point of inflection occurred when x was 1. So we need to find that corresponding y value when x was 1. Okay. So I think these are all the parts. So then I'm going to go here to my y equals. We got this e negative 2 divided by x. Okay. 0. Let me see that y value. When x was 1, that's some fraction. E to the power of negative 2. Okay. Okay. So then to get a proper window, let's see. Let me see. Let's go like negative 1 to like 2. Let's go in steps of like, let's go 0.25. Y minimum. Let's go negative 2 to 2 in steps of 0.2. We might need to zoom in more. Okay, y value. Let's go negative 1 to 1 on the y-axis. And let's go in steps of 0.1. So I'm zooming in more. Okay, look, there's an asymptote at 0. Let's see. Oh, when x is 0. Okay. Guess that makes sense, yeah. Because we can't divide by 0. Yeah, okay. So let's back up. Yeah, I'm tired. Right here. For the vertical asymptote, even though we can't make the denominator 0, we still can't divide by 0. So that x in the power, we have to throw out x equal to 0, right? So we do have a vertical asymptote at x equals 0. because we can't divide by 0, even with that being in a power like that. So I'm going to augment that. This one, I'm going to change it to x equals 0. Let's see. Okay. All right, so let's see. We got x equals 0 there. Horizontal. E to the 0 is a 1. Double negative is positive. E to the 0 is a 1. Okay, y equals 1. So let's see if we can see that. Okay, it does like it like levels off. But it doesn't go to negative infinity. Let me see my window. Y. So instead of negative 1 to 1, let's zoom out a little bit more. Let's go negative 2 to 2. That was kind of far. We did try that before. Let's go negative 1 point. Let's go like 1.3. 1.3. Okay. Still kind of tough to see. I feel like something's off there. Let's see. So again, that vertical asymptote, we got what, x equals 0 there. Well, see, I'm not confirming this horizontal asymptote. So what I'm going to do, I'm going to go to my y equals, I'm going to do y equals 1. I just want to see that. Okay. So we might just need to, our x probably just got to go a little further out. Like, let's go out to like 5. Yeah, you can see it flatten it off. It is approaching 1, right? So let's go out even further. Let's go out to like 50. Right? It's flattening it out. It's approaching y equals 1. Okay. 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 Now, negative infinity to 0. Why is that not showing? When x is negative 1, yeah, it should work. Let's see. So let's go negative 30 to 30. Let's go in steps of like 3. Hit graph. Okay, there we go. Okay. So, okay. We do have a horizontal asymptote. Vertical, it does look like we have a vertical. Okay, let's change the y value. Y, man, let's go to y max is like 3. Okay. Okay, so we can see our vertical asymptote. Okay. Okay, so now we're starting to see things. So let's see. Increasing from negative infinity to 0, we confirmed it. It's increasing. And from 0 to infinity, right? Okay. We got that it's decreasing. So decreasing as we trace it left to right. We don't have it decreasing anywhere. No local extrema. We can confirm that. Concave up from negative infinity up to 1. Maybe that should be 0. Second derivative. I think I'm missing something with second derivative as well. We got our 0 there. Why did I put 1? Concave up, concave down. Because there is like a little gap. 0 to 1. Point of inflection. Because when x is 0 and 1. There might be something going on. We have to like zoom in. I'm like, I think I'm faded. Well, not I think I am tired. But I was trying to push through because like I know I'm kind of at the end. The second derivative. Something's going on there. Concave up, concave down. When x is 0. So like if we did a half into the second derivative, that's positive, positive, that's -4, but then that's going to be still what? A positive. It's concave up. Yeah. Then all collapses to 0. Oh, at 1. So I need to be able to see, like when x is like a half, I need to zoom in. Because it might be doing something funny. Like how is it going from concave up to concave down? I need to zoom in. Maybe I should use GeoGebra. I can see it better. Let me zoom back out 3. Need to change the window. Because I got to zoom into the origin just to see what's going on there. So let me see. I think I'm tired. 1. Let's change it to like 1.75. Let me see what that looks like. I think it's something strange is happening between 0 and 1 that we're not seeing. Okay, let me try this other one. Well, I just don't feel like doing it. I'm just trying to think about that. That's the last part. Because I'm not confirmed. I mean, okay, so we can see where it's going from like concave up to concave down, but we're not able to see. Let me see my window on my X. Okay, I'm going to zoom in. So let's go like from -2 to 2 on the x-axis. And we'll go in steps of like 0.5. Because I'm trying to see what's happening between 0 and 1. Yeah, it is behaving weird. But I'm not seeing the graph unless it's just starting. Is it not defined for like between 0 and 1? Let's go back to the original. Okay. So like if we did a half, if x were a half, let me calculate. Okay, what about a quarter? So it seems like, and maybe we can zoom in some. See, these are really, really small. It seems like, okay, it's kind of like doing a little dip, but if it's doing a dip, then we would have a minimum. See? Let me go check here. Because that's going to make that 0, but we get a 0 from there and a 0 from there. Oof. Yeah, I just need to zoom in more, and I'm just not doing it. I think I'm just tired. I'm trying to confirm all the parts. The only thing I'm missing is when x is between 0 and 1, showing that it's concave. Like everything else is there. Concave up for the left of 0, concave down for the right of 1. Let me see if I zoom in some more. Change my y value. Let's change that to like 0.3. And the scale is like 0.01. Okay, let's see if we can see something going on there. So you can kind of see it. Oh, let's see, y minimum. Okay, so let's change that to like a negative 0.3. Nope, not negative 3. Okay, let's see if that gets us to see. Still looks weird. But you can see where it kind of does this little weird dip. Let's see. Sorry. Okay. Yeah, you can kind of see it there. Okay. Well, we confirmed most of it. It's like I say, it's a little bit off. It's 2 in the morning. I'm spent. I thought we was doing good until I think I just burnt out. Um, But yeah, so we're not getting a local extrema, but we are getting it going from concave up to concave down. For that concave up, they might accept it as, so as an alternative, I'm just going to put it like this. Negative infinity to 0 and 0 to 1. Maybe. Like that might be the result. Where'd it go? Yeah, sorry, I'm about to fall asleep. But that's most of it. So we can talk about it a little bit later too if we need to. So okay. Yeah, that's so strange. And then it would kind of help if I can see like their options for their graphs. Because it is kind of behaving like a reciprocal function, but it's a little bit funky between 0 and 1, but everything else is fine. Okay. And so with that, we're going to end the session here. And now from one beautiful mind to another, take care. Sorry about that last part, but I'm tired. All right, take care. Peace. right, so that concludes our series of the 5 questions from calculus for this evening. Sorry about that last part. Like again, it's like 2 in the morning. But yeah, we did the best we could. So just try it out. If you find errors, just let me know, and we just reach out to me, and we can like, you know, research and dig and try to get to the bottom of like any kind of confusion. Because I know it wasn't the cleanest, but you know. So just let me know, and with that, we're going to end the session here. From one beautiful mind to another, take care. Peace.